So today is the second lecture of the deep learning module, and I'm going to talk about the deep generative models, which is probably one of the most popular thing nowadays in this community. You know, if you look at the conferences like CVPR and ACL, these NLP and the CV conferences, it's not exaggerating to say maybe 90% of papers is about deep generative models, GAN models, VE models, and so forth. Even in mainstream conferences like ICML, NIPS for machine learning, a huge proportion, more than a half, is about that. Why it's so interesting, and what are the remaining problems? Again, you know, on campus we have a couple of deep learning classes telling you how to massage, how to play with these kind of models. I'm not going to repeat all that. Okay, I'm going to give you the less kind of directly usable, but hopefully more unifying and cleaner theoretical underpinnings of these models, so that you can see a unity and some connections. So what is a deep generative model? I think people probably, you know, were inspired by a picture like this, right? Say you want to produce contents, such as, you know, painting, for example, and this is a authentic picture, and that's a Van Gogh painting, and then you want to create some kind of a Van Gogh style rendition of the picture, and now deep generative models can produce something like this. You kind of can see that, you know, the shape, the context, the texture, the color gets morphed into a particular style. Okay? Similar operation can happen in text, in music, in a lot of things. Of course, there is a big issue about how to determine it is good or not. Did you achieve your goal or not? That's very subjective, especially in the space of painting and music. It's more subjective, especially in music. In fact, a noise can be called music, so you know, very hard to evaluate. But in text, you generate an article, if it's nonsense, people can really tell it. Right? So there are some different studies also about how to evaluate. That's not the topic today. We're going to talk about how to produce this content, you know, and what's the theory behind it. So again, going back to history, deep generative models really, you know, are probabilistic distributions of random variables, right? And you can use it to sample, basically, instances. And this word deep really means that you have multiple layers of the hidden random variables like this. Okay? And a few examples. We learned about last time, you know, the sigmoid belief networks, in which, you know, the lower layer connects to the upper layer by a sigmoid function like this to define the conditional distribution. And so these are really very kind of authentic and genuine probabilistic models. And you are really using the Bayes rule. You know, there is a joint distribution of the whole thing, which is factored over P of xi, given xi of pi of I, right? And then the bottom layer of the visible can be produced by marginalizing P of x of x minus the v, something like that, right? And therefore, this is the distribution you sample the image or the whatever downstream from. So that's a deep generative model. But even very early in the history, this very kind of clean and principled idea is already getting twisted. For example, here is an early example of the neural network models that is deep. It's called the Helmholtz machine. Okay, the Helmholtz machine is graphically, you know, expressible like this, but this graph is not meant for already, you know, presenting a distribution or a unique distribution. It is actually used to, you know, record or document two computing processes. Remember, we say that deep network at some point becomes a computing graph that helps you to organize or express a process of computing, right? So this is the case. You have a generative bias expressed by some hidden random variables there, and then through a sequence of generation process, which could be a probability distribution, using these weights as the model parameter, you get some kind of data. Or if you already have data, then assume the data are produced by this process. Therefore, the data could be called the inputs. And then there is another process. So here we have the P of theta of the x. And then there is another process, which is a P of the hidden, okay? And the parameters by phi, which is called an inference model. And this inference model and that generative model may or may not be related. Okay, typically, in the classical world, the inference model is a posterior of basically the hidden given the x. But it doesn't have to be. You can have any inference model taking the inputs and going up, and then you kind of using that as some link to put them together, alternating the inference and learning methods. And this process, not the global mass expression, which is missing, defines the model. Okay, so that's a Helmholtz machine. There are actually even, so this is about the computing process. You also, again, don't need to even use only this approach. There are other ways to define a deep generative model. One of these is called predictability minimization, which is a training procedure. Okay, it's just not just the two computing process. It's a training procedure that is even more interesting. It was again invented by Schmidt-Hatter, a long time ago. So the idea is that again here my goal is to learn the latent representations of some observation data. Okay, and then I want the learning effects to achieve a particular the learning outcome to achieve a particular effects, which are the predictability of the latent variables. So he wants to, this model is like this. I'm going to learn these three latent representations. And then I also define another three representations which mirrors this. Okay. And then every time I'm going to use these two learned things to predict that. Okay, and I want the learned outcome to be minimally predictable of that one, which is not included in the inputs. And I want the predicting machine itself to be maximally able to predict. So there is a tension. Okay, the inputs are minimally predictable, but the machine you use to predict are maximally predictable. And then you do this for each of these mirror, with all but one of the latent variables corresponding to that predicting nodes. So that's why it's called predictability minimization. Okay. In fact, you can see this idea was kind of similar to the other idea used in the generative adversarial networks, which we are going to talk about in a second. And there was a huge debate between this author and that author, in both private and public venue, to claim credits of this whole thing. Okay, still not resolved. You can see there are some similarities of the idea. One is, learning a representation and then qualified representation using some kind of additional loss functions. There are two loss functions out there. Okay, that is kind of playing against each other. So this training procedure could also define a model. Again, implicitly, there is no equation that you can use to define what is this model. Say, writing down the posterior of this one, given other one. Such thing doesn't exist anymore. Okay, so these are the early forms of deep generative models. You can see they were all invented, 20 to 30 years ago. It's very, very, classic, old in a sense. But a word model already, ever since then, is already, not very rigorous. Okay, and then learning procedures going with that, not going with that in an independent path, is also evolving in some very weird fashion, which actually could sometimes cross into the definition of the model, either to inspire them or to give them the vehicle for learning and inference computation. So here we can see a few examples. So such as, for example, we know that to train a deep generative models, you could directly use sampling procedure. Basically, training is about filling in the latent variables, and then using an EM type of idea to learn the parameters and so forth, right? So you could just directly infer the hidden random variables given the observation using a set of model parameters, which is probably the posterior of the model given the data in this case. And then this is called data augmentation. Okay. It's asymptotically exact in getting down the true model of X given all the Z's. Right? And then we learned a technique known as the variational inference, where we introduce an auxiliary distribution called the variational distribution to approximate the posterior of that, P of Z given X. Right? And then you are going to learn the best two sets of parameters. One is the theta, which is the original generative model parameter. But now you have a new set of parameters, phi, which is the parameters of this inference model, or the variational inference model. And then here's a loss function, which we already shown using the Jensen's inequality that they are the lower bounds of likelihood. Right? You may always, so maybe I'll give you a very, very kind of intuitive example, just I came up with today when I drive. Why, what's the core difference between this and that in terms of the intuitive idea? Why we need an auxiliary? Say you climb a cliff. You could just scale up directly. If you are a master, cliffhanger, we saw some movies, right? It's a solo free, something like that. Will give you kind of a idea about how to climb this directly, right? Like this. And then there are other ideas which, like, what if I'm climbing? Sometimes the experienced climbers want to go into a crevasse, inside that surface, because now you can go this, that, bounce back and forth. That sometimes makes the climbing easier, right? Right. So this thing is basically the other side of the cliff. It gives you the stepping stone to go back and forth, right? So you kind of can see that the sampling corresponds to this idea, and this one corresponds to that idea. Okay, and they, of course, could be, this one could be a little bit inexact, because what if this whole thing go the other direction? Then you kind of go somewhere else. Okay. Now, that's the two ideas, which at least has a very clean mathematical picture. Then there is a third algorithm, which is kind of weird, called weak sleep. Suddenly, at least these two things are having the common goal, which is to maximize the likelihood of the data. This one, it's also using a alternating step, but somehow you can see that the loss function in the alternate step become different, as I'm going to explain. You can already see the differences. Here, no problem. We're learning the generative model and the inference model. But in here, the loss function become different. It's like when you go here, you climb there. When you go here, you climb there. So what is this? I don't know. Okay, sometimes it's lost. And in fact, all these methods actually being used later on to compute or to even design the model itself. But with all these early efforts, there is now a resurgence of deep generative models. Again, starting from the RBM, we knew that the RBM, is equivalent to an infinitely deep thick-mode network, right? That's, a deep generative model. And then we have a few others, like deep belief networks and the deep Watson machines and that. You should go back and read about the discussion. Then at about 6 years ago, we kind of ran into the first modern day actively used deep generative model known as the variational autoencoder. Okay, so here, in fact, the ideas are all old ideas, but somehow the execution was excellent. Then it produced some very nice results. So the model looks like, you have hidden variables, you have X, then there is a generative model. Again, very, very familiar idea, but this generative model could be very, very deep. Okay? And then here, again, go back, you have the posterior of the hidden random variable given the X. You call it an inference model. And again, this inference model is also very deep, many, many, many layers. These two models doesn't have to be symbolically or algebraically equivalent as conditional and posterior. Okay, they can be different. They are learned with a shared loss function I'm going to show you in a second. And then that's the deep generative model. Okay, it's very, very similar to what we see before, but it's using a variational inference approach, minimizing a loss. And then almost the same year, in fact, it's about, the same year, Goodfellow and his advisor and collaborator invented another model known as the generative adversarial network model, which is even more mysterious. So here, basically, we are going to, have a process. It's a process that starts from some hidden codes, or they call them code. It's actually latent random variables. But this code doesn't have any meaning. It comes from a uniform or Gaussian distribution. And then there is a kind of a transformation process. Okay? And this whole thing is now defining a generative model. It's not really a model because it doesn't define a very explicit distribution. Here, you just can imagine 100 steps of transformation with multiplications and transitioning, convolution, and all that. And then you produce some data. And then there is another kind of here you have a model called a discriminator, which will compare this with that, which is a database of real data, say images. And then you decide whether this generated image is a fake or draw from here, because I didn't tell you. If it is a fake, you reject it, and given this whole process a low score, therefore they need to improve the theta. Otherwise, you accept it. And also you learn this phi so that this discriminator are becoming better and better, smarter and smarter, even though this phi is becoming also better and better. So this is similar to the predictive minimization machine that we talk about in terms of the spirit. Right. So this is called the generative adversarial network model. And then again, there is a whole kind of sequence of other models, which I'm not going to even draw a graph and discuss about. They are all combinations of earlier ideas or newer extensions. Okay? So we have a zoo of such models. And before I start to dig into the math, I want to clean up the notation a little bit. Again, as I mentioned, this community of deep learning is, for whatever reason, very, very free thinking or maybe not conventional in terms of naming their creation. Maybe one of the reasons, I guess, is that many of the innovators are very young students like you guys. They didn't read the literature enough yet. And therefore, they didn't realize some names have certain meaning. But on the other hand, they are very, very intuitive and creative. They can actually grasp the essence of what is being created. So now you see all these new names. What is known as the posterior distribution in the literature of statistics, which is also known as an inference model in early day machine learning, and also variational approximation in describing these kind of models, now have the following list of names, partial list of names. It's a list actually goes longer. But when you see something like a recognition model, inference network, recognition network, probabilistic encoder, these are the same thing. Okay, they all mean a posterior distribution or something close to that. That's basically this part. Okay, the inference model. Okay, and then the model, sometimes it's called, which is a prior times a conditional going from top to bottom, which is also known as the generative model or the likelihood model. Now has all these names like generative network, a generator, and decoder, and so forth. Okay, so yeah, it's a little bit difficult. Create some difficulties in, helping people to connect the dots. Hopefully, you should be at least familiar with all these things. In fact, I may be also interchanging between different words in the subsequent lectures. Okay, so now let's dive into the math. For all these models. Let's begin by what we already know, variational inference. Just to recap, variational inference is about learning this whole thing for the hope of learning this. Okay, you want to learn P of theta, which is the model, and you use a stepping stone, the PQ of phi, to be the ladder. And then, the goal is to, the trick is to now, instead of learning this, you define the lower bound of the likelihood, which is also known as the free energy, like this. And then you are going to start a alternating procedure, like the EM. In the E step, you maximize that bound with respect to the inference parameter phi, with the generating parameter theta fixed. In fact, symbolically, you can even come up with a closed form expression, okay, like this. Okay, but of course, in practice, it is very difficult because here I'm talking about proportional. The normalization is very difficult, and also this whole thing can be also very complicated if you have a huge network. And in the M step, in fact, it doesn't make any sense to call them E and M anymore because both are M or M, right? So. But we are trying to draw correspondence to the EM algorithm. So in here, you hold the inference parameter fixed, meaning that your hidden variables are all imputed. And then you're going to treat them as all observed data. You learn the generating parameters. So very, very clean idea, right? There is a single loss function that is used all the time in different procedures. Now, wake-sleep algorithm. I found it, it's actually published very early by Hinton in a science paper. It's a very high-profile publication, in fact. But the math was very, very murky. Okay, so it is essentially doing the same. I'm going to learn an inference model. I want to learn an inference model, and also a generative model. You still find these two terms here, but it turns out that the loss function, that I used to learn, which is supposedly this, the free energy, gets somehow changed. It's like I'm climbing this, but now I see this, and somehow if I'm here, I start to pursue another goal. Okay, and I'm hoping that they may eventually kind of go together, but I don't know. I'm going to pursue a local goal, nevertheless. And here is how the goal looks like. You can see that, in fact, if you don't have a sharp eye, you may not even realize the goal is changed. But you can see the part of the loss function, which is a KL between the inference model and the posterior, which you want to minimize the KL, becomes now measured differently. It's reversed. Okay, why that's the case? Well, it's actually because of laziness. It's because of a computational convenience. And here's why. So my original goal is this, the free energy, which is expressed as a constant plus a difference between the posterior and the inference. And in one of the steps where I want to hold phi constant and do theta, and the equation will be reducing to this. You need to compute an expectation of that. okay? And then what do? Expectation of this term over that. If we are in a convenient world, we sample from this and do summation, right? So you need to sample from this inference model, hopefully from the previous step. And this is also known as what? This is known as the weak step, because when you sample the Z, you are using the observation X, right? Therefore, you are awake. You actually are knowing about the environment. The next step becomes a little bit tricky. Okay, if we look at the original loss function, and I minimize this with respect to phi, it turns out that you need to compute, a gradient of phi from here. Why need to have gradient? You may say, why don't I just sample and so forth? Well, look at this term. This term, KL, is actually about what? It's about expectation with respect to the Q of Z, Q of X. Well, no, let's say Q of X and Z over phi. You need to use that as a V equal to compute expectation. And also, you need to have the Q of phi divided by P of theta. Okay, whatever it is inside. Right? You can see that this target of optimization phi is both in the argument of the expectation and also in the distribution that you need to use to take expectation over. Therefore, you cannot sample it. You are learning it yet. Right? So that's becoming not easy. Therefore, you have to do a gradient. You directly take gradient of that, which gives you this equation, which after a few steps get you this equation. This is becoming trouble-worthy. It looks like a benign equation that you can still need to compute, but hopefully it's becoming a little easier than that. I don't know. But this one exposes the difficulty about even if you can do that. There is a logarithm over a distribution. Logarithm over distribution, you usually don't want to take it as it is without some other transformation, because if you have a probability of 0.001, for example, when you put the log, how big it is? It's very big, right? And the probability usually are very big because you usually have a deep models. You need to multiply multiple, between 0 to 1 things. Therefore, this number is very big. You end up with some quantity, which is the gradient, that are extremely variant. Okay, so that's basically what this Monte Carlo estimation, impressed people. Okay, it have arbitrarily large magnitude, therefore it have arbitrarily large variance. Therefore, the computation just cannot go through. Okay, so that's actually how people find this algorithm to be very difficult, or the variational inference to be very difficult. Okay, so then Hinton et al. Find this a very interesting idea. They say, okay, this one is really, really annoying. It's very difficult and generating high variance and so forth. How about, I forget about it. I'm going to now swap this. Swap this basically means that now in this case, you need to only sample from this distribution for the Z and X, okay, and compute the expectation of that. There is no such a kind of arbitrarily large scaling term, okay, in this whole thing, okay. But in here, you can see that first of all, my loss function is different from the original one, and the procedure also becomes now sampling the X, which was actually in the data. I try to ignore the data. I'm going to sample from the previously learned generative model, prompted by theta. And that's why it's like dreaming the data rather than collecting the data from real world. Okay? And you can do this top down. Okay? So that's basically the wake sleep algorithm. Okay? It has a procedure which do the dreaming step or the sleep step and also the wake step. But mathematically, it is also change the target already. Okay, you change your pole already, and you get some results, which at that time was, in fact, the reason why this algorithm wasn't very popular is because if you present it to a statistician, they laugh. Okay, hey, what are you doing? Somehow you change your pole already, and you are still trying to run a procedure, and what do I get out of it? Well, at that time, because the models are all shallow and not very interesting, obviously the model isn't getting you a good result. If you measure the accuracy of this model against some other more expensive but accurate kind of a procedure, this one doesn't have advantage. Okay, basically it's been wrong but not been too wrong yet, so that you don't see crazy results. Now, if you have a deep network that is very, very deep and will make you very, very wrong, in fact, you could generate a crazy picture. Some people may like it. So that's something was expected at the beginning. Okay, so that's wake sleep. There's a recent approach which actually do this job in a different way, that give rise to another model. But again, I want you to make sure you understand this a different thing. Okay, I'm going to cross off the original loss, which is correct, and replace with an incorrect loss function. Okay, so this is comparison, VEM and the wake sleep. And this is an important picture for you to remember. They basically all want to learn this, the inference model. And then, there are both two steps, E and M, wake and sleep. And in the wake step, they are very, very similar. Okay, targeting the same loss function, KL, between the inference and the posterior, and learning basically the inference model. But in the sleep algorithm, I changed the pole. Okay, just to repeat. And of course, it gives you all these benefits and low variance. You can sample from the generative model and so forth. But it's too objective, and it is not guaranteed to converge. It may converge, but it may not. Okay. And this one guarantees to converge because it is it's a fixed point equation that you have a single kind of a convergence point. Okay. Now, that literature brings us to the modern day deep generative model known as the VAE. What is the VAE? It's very hard to determine whether VAE is a model or it is a process or it is a Oracle protocol. It's very hard. It's the whole thing, including the model and also the way to compute it. The key idea is this. Again, you want to do the inference model, and we knew that in the inference model, learning will have this explosion of variance and so forth. We didn't like it. Instead of changing the pole as did in wake sleep, what Max Wheeling et al. Means, quite a few authors actually in that same year, around that time, came up with similar ideas, is to reparametrize. Okay, reparametrize this inference model to make it easier. So it's a very, very trivial idea. In fact, we do reparameterization all the time. In our, for example, if you generate a Gaussian distribution from a uniform proposal, if you look at the MATLAB code or our code, it's about reparameterizing the model, okay, and turn them kind of into a mean and variance that you like. So in here, instead of using a heavily parameterized inference model, I'm going to assume this one is the original thing. I'm going to now use a new idea, which is that I assume a noise generator from a trivial distribution like a standard Gaussian, and then I'm going to do a deterministic transformation, okay, from the noise and also the input into Z. Okay, this is my reparameterized approach of this. So in a sense, it's instead of a arbitrarily kind of composed deep probabilistic model or network model, I'm going to basically take a particular way of writing this model, which is starting from a noise and then using a deterministic multi-layer transformation. And if that's the case, suddenly the derivative, the gradient, okay, with respect to the inference parameter phi. By the way, the inference parameter phi now is no longer the numbers in the probabilistic distribution. It is going to be the transformation parameters, okay, weights and so forth in this process. The parameter, the gradient of this with respect to those parameters suddenly now take this form, okay, which does not have that arbitrarily large scaling term, okay, which is the log of some probability. Okay. And so that's actually giving you a proper kind of a lower bound of the gradient, okay, at least empirically. It doesn't guarantee you absolutely have low variance, even though the expression here doesn't have that big term. But in practice, when you produce, you still may not have control. But at least mathematically, they are not changing the loss function. Okay, it is a reparametrized, a particular inference model. And that's basically the variational autoencoder. Okay, so mathematically clean and computationally not too difficult, and that's the protocol. And the mathematical cleanness also comes from the authors of this model. Max and et al., they were trained, originally as theoretical physicists, and they are very, very, very deeply rooted in, the mathematical literature, statistical literature. They kind of want to deviate least away from that principle by using some well-understood tricks, such as reparametrization. Now, look at the results. After I train this model, P of theta, okay, by the way, training P of phi of z is about helping to train this, right? So eventually they get this. And then they start to not only just estimate the correctness of the theta, they actually want to see what kind of data I can generate from these models. And they tried images, which like this, it's kind of not very satisfying. It's blurry, right? You can recognize it, it's not very satisfying. Honestly, that wasn't a very impressive result when the paper was published. Text was a little bit interesting. Because in our visual world and verbal world are almost opposite, right? When you draw or take picture, you want them to be focal and sharp. When you speak your language, sometimes you want to be ambiguous, right? You want people to guess and so forth, or you want to avoid being vulnerable. So, for example, it turns out that when you ground the model with these two observation sentences, so I want to talk to you, and she did not want to be with him, and so forth, then the sentences generated from this model is like this: I want to be with you, I want to be with you, I don't want to be with you, I don't want to be with. Things like that. Something in the middle start to happen. So that's just an observation. People actually don't know why that's the case. Very quickly, another model, which turns out to be complementary to what I just observed, what we just observed, which is known as the generative adversarial networks. It has two main components. One is, again, the generative model. There isn't an inference model in this particular prescription. No variation, no inference model. Pure generation. One latent code coming from some prior, and then one transformation, as I said, and then a discriminator. I think I said this before. And let's just look at it more graphically, right, to expose what you need to learn. You need to learn the generative model like this, and you need to learn it such that we should beat the discriminator as best as possible. Right, so that's a loss function to basically describe that ability to beat the discriminator. You also need to learn the discriminator, which is to really do the best job possible to correctly classify the sample being real or fake. Okay, very, very interesting interplay between the two things. And as a vehicle, you actually need to involve a real data set, which defines, by the way, an implicit distribution. and then you need to have this, and then these two will be kind of played against each other. Okay. Okay, so this is the, there are some caveats in terms of addressing mathematical issues like vanishing gradients and so forth. Therefore, instead of minimizing this guy, I'm going to maximize that guy. That's just kind of a little technical details that you can go through by yourself. Okay. Now let's clean up the mess of the GAN model because it looks so different from everything else. When it's first proposed, it was a little bit confusing to people in terms of what the heck this whole thing is doing. How can I even analyze that? Whether it is so at that time you can see in the early days the only way to qualify a model. I believe there were some apps, a crazy amount of apps coming there giving you all these rendered pictures and all that. And each one called them to be a good model, right? I mean, that's the only way people can do it because math is unclear. Then, of course, I look at the quality of the image, and it's interesting that it's good, right? Okay, so, but there are some kind of important kind of concepts that people start to realize. In this, basic formulation, you already can kind of see, what is the optimum result people can achieve, in optimize the whole thing, the learning framework. If your generating process is becoming identical to the data distribution, obviously you get the best result, right? You can maximally cheat the discriminator. And the discriminator, again, can do best if it is assigning random probability of each side. So that's kind of people see, okay, this is kind of a triviality that you reach optimum by achieving that, which is at least know where the target is, even though the results is not necessarily easy to achieve. Now, interestingly, the picture being generated from those are very different from VAE. One thing we see that is they are sharp. Okay, they actually are visually acceptable. But people also see, which is not shown here, that they are very narrow. Okay, they usually pick up the major modes in your data set. In this case, bedrooms and almost all bedrooms, maybe a few, living rooms and so forth. Even though the data set may have many other things. So in a sense, the generation are focusing on a few areas on the whole thing, as people observed. Okay. So I'm not going to go on and on because there's a whole zoo of deep generative models, okay, and a huge kind of enthusiastic, community creating every year many variations. And without too much enlightening, story or connection on the mathematical side, and that's where this criticism of this community being alchemist. Come up. In fact, I might be the first to invent that word in Alchemy, then picked on in other conferences. I gave this picture as early as maybe 2016 or something in one of the summer schools. And we machine learning people want to be the chemist, right? We use a periodic table, and when we put elements together, first of all, by looking at where they are in periodic table, we know whether they can come together or not, whether their electron orbits are complementary or not, right? Sodium and chloride could come together, but sodium and chloride and magnesium cannot because they are not, compatible. And also you can calculate or maybe can predict what's the physical properties like hardness, temperature, and so forth for that, right? So that's the good about that. But right now, as an alchemist, you mix, you try, and you may sometimes blow up your lab. But if you're lucky, you get something very interesting, right? That basically is what's needed at some point for this whole body of research. And so, in the next few minutes, I'm going to give you one such effort, that helps unifying some of the the models that we learned so far. And this is based on a paper written by one of my students and also many follow-up works. Okay, so let's take a kind of top done more kind of a holistic view of all the deep generative models and see, first of all, is there a way to even make their expression look a little bit similar to each other? Okay. For example, this is the GAN model. And this is the best effort available at then to describe mathematically what a model is. Right? There should be an indicator function which indicates whether the sample X is from a oracle or from a data set. In a sense, you can, in principle, write down a conditional of the X given the Y. Even though that conditional can only go this far. You cannot put an equation there anymore because this one does not have an equation. That part is a transformation plus a noise, right? So there isn't anything to write. And then your sample basically come from these two. You can draw samples in these two ways, depending on the value of the Y. And the code space in this case is degenerative. There is no kind of a code needed if you draw from real data. So this equation is fine. It's operationable, but it's very different from our entire literature of, say, variational inference, likelihood-driven learning, and weak sleep, and so forth. Okay, so now one effort that is done is to rewrite this equation, okay, with a new formulation. And here is the new part, the new formulation. First of all, we introduce the implicit distribution of P of X given Y. It is implicit, because beneath that there are many steps, but symbolically you can write that. And then this one, you could call it a generative model because you are generating the examples, okay, from some maybe hidden variables or other indicators. And then there is a discriminator. There isn't a counterpart in the literature corresponding to discriminator. We have inference model, but not discriminating models. Right? So we parameterize it this way. So don't mistake, this one is not the earlier inference model that we used in VEM and weak sleep. It is a discriminating distribution. Okay, Y given X. In fact, a shorthand for this is to write a reverse of that, which is to indicate the other sign. Okay, it turns out that by introducing these little instruments, you can now rewrite the original set of loss functions into a new form, which is like this. In one step, you learn the discriminator by maximizing this whole thing, which is an expectation of the discriminating function and with expectation to this, okay, which kind of look like a posterior or inference of the hidden states. Because Y is always observed, you need to, at the end of the day, determine whether it is true or wrong label. And then the other step is to learn the generative model parameters, okay, which is here. But it turns out that the loss here is not quite the same as this. It is the reverse of that. So you can see a flavor of this to the weak sleep, that in two steps, I'm not using the same loss. It's a different loss. At least this one looks a little bit more similar to the weak sleep. Okay? In fact, I do a comparison here. The GAN objective and the variational EM objective. By the way, I think in one of the early slides I didn't explain, but you should know. There are different ways to express the variational EM loss function. One way is, I believe it's like this. It's like you have two terms. One is the constant term of likelihood. The other is a KL between the inference model and the posterior model. But the other way is to express it as the KL between the inference model versus the prior of the latent variable. And then here there is a term that is on the log of the likelihood, x given z, expected over, the the inference model because it's conditioning on the inference algorithm. So this term is sometimes known as the reconstruction term. Okay, it tells you how good you reconstruct the visible data, conditioning on the hidden. The hidden one requires you to draw in that inference model. So it's a nice connection. Okay. And that's basic Variational EM. Then we know that we need to learn these two models. Again, remember this term: generative model and the inference model. They are optimizing the same laws. Now, after rewriting the GAN model, you kind of see a similarity, this part and this part. Right here, you are also going to now optimize over a distribution of a y given x. In this case, it's x given z, but in that case, it's y given x. Well, one way to draw a connection is that the y here actually corresponds to the x in here because they are all observed. Okay, y here is the label, and here x is the image. But here, in GAN model, the image, you don't have it. You need to generate it. Therefore, it is not observed. Therefore, my x becomes the hidden, corresponding to the z in here. So in a sense, they are similar to each other. And then the thing that we use to impute, the hidden variable, in this case z, in that case x, is very similar. It is the inference model, basically, right? But there isn't a term here, for that part, which is the KL between the posterior and the hidden, the prior, because in GAN model there is no prior of z. It's just trivial, right? Okay, but the other differences you may notice already is that here, the two steps hits a same loss function. Here, there's a little differences. Okay, there is a little r here, which gives you two different losses. Okay. Okay, so that's the relationship between VEM and the GAN. Okay, now, why I do all this? Why this connection? Just because I want to connect them, or I can draw insight from them. Usually, when a legitimate researcher, build a connection theory or a unification theory, the connectivity and the unification is not a goal. Okay, it is a vehicle to get something out of it. For example, by making connection between the GAN and the VEM, can we learn something more about what's happening in the generative process of GAN, which we didn't know? For example, why GAN pictures are sharp, why they pick on a few modes but not other modes, right? In this literature, there are a lot of theoretical analysis about why about that, because there are the vehicle for all these equations people understood very well. Now, by having the equations in the GAN community similar to this, maybe you can gain some more insight, and that's what we're going to do. So remember, in the VEM, community, there is a different way of expressing that, which is to really just put the learning target, the inference model Q, in a single term, which basically can expose the trend of this particular entity, the inference model, during the learning. Because you are iteratively learning this objective, if the goal is to minimize the KL in there, then you can see the trend. It is approaching the posterior in every step, measured by the KL divergence. Okay? In here, it's a little bit harder to say because you are in here and there are two terms, right? Now, can we go further from there to make the procedure even more interpretable as we do in EM? Well, a lot of math, but I guess you could basically save all this to your homework reading. But I want you to focus on this. This is a lemma that's proven in the paper, which is very interesting. Instead of just looking at a whole kind of optimization problem, let's look at a particular step, okay, in that optimization. Say we start from the last step of the inference parameter and the learning parameter, phi 0 and theta 0. And let's look at how the update look like, okay, in a single step. The update, of course, the magnitude of the updates is defined by the gradient, right? And it turns out that the gradient of this whole loss function, which we wrote down already in the previous slides, with respect to theta, looks like this. It's very interesting. In here, you can see that it is a KL between two terms. Okay, this is what? This is actually the posterior of the x given y. Y is the observed label, being from true picture or false picture, and this is the distribution of the pictures. And this is our inference model, right? Which is in fact it's theta, but which makes them look like a generative model from the z to that. But we can also call them the inference model because it is defining the current form in action of the x being generated from the y. Okay. So it could also be understood as inference. So it's measuring these two distances. One is a evolving model, the other is the reference model. Jensen's inequality, we don't care about that because there isn't any variant form as a result of the updates. Okay. Okay. Why this is interesting? Okay, let's look at how each of these terms look like. That requires a little bit of math. Okay. Well, here are some definitions. I just want to again clean up the nomenclature a little bit so that you are all together knowing what we're talking about, right? So this one we can call them a prior distribution. Parameter set to the original, the previous estimation, and for only the image, the x, call them prior. Then given the label, which is indicating truth or false, whether it is a true image or generated images, you can basically fold this into a posterior of the x. Okay? So that's the posterior. This is our variational distribution. Okay? And our lemma 1 tells that I want to minimize the distances between this and this. Clear? I can now start to plot this. When we are here, we start to look like where we are doing in the VEM algorithm, where you are basically closing the distances between the two posteriors or two distribution of the hidden random variables. In that case, the z. In this case, the x. This part is very important. I actually start to plot what is the posterior and what is the inference model. Okay. The posterior, forgetting about all this other very hairy math, okay, just recap this equation. Right, we know that. And you can show that this green stuff, which is the posterior, conditioning on the previous estimations of the phi and the theta, is what's plotted in here. Okay, it is literally a mixture model of the data distribution, the empirical data distribution that you don't actually know the form, but you have the data, and also this guy, which is the inference model from the previous step. Okay, how to get there? There are derivations in here I'm not going to explain, but this one is a mixture of these two as of now. Okay, and then you want to basically, do an update of the green distribution. Okay, so that do an update of not green, of the red one. Okay, so that they move from this step to the next step, to this one. Okay, which is the inference model. And then your distance is. Do I have an equation here? No, I don't. The distance is measured by the KL between this guy and that guy, right? Therefore, you want to now move the green, to a mixture model, of this newer version of the data and also the posterior from the last round, and you get something like this. right? This is theta equals to 0, and this is now theta become a new one. Get it? Okay? So your moving target is to really change this green stuff so that it becomes closer to the mixture of the blue and the red stuff, and that gets you there. Okay. And the closeness is defined by what is known as this KL divergence. Okay, it's remember, if you remember, well, maybe you don't. KL is a asymmetric measurements, right? KL from A to B is different from KL from B to A, right? And in this case, we are using the forward KL, where the moving target is in here, and the invariant, the reference party is in there, and that kind of KL captures, forces the argument, the red argument, to be capturing the major modes of the ladder. I'm not going to show that. It's well-known facts in the statistical literature. In fact, if you put the green stuff here and the red stuff here, then the KL will be doing a different way of matching the whole distribution. Okay. And therefore, because it is only capturing the major mode, but not many other modes, you see that this new estimation are missing some of the modes. This particular mode is now missing, and the bigger ones are captured. Got it? This red thing now becomes this. Okay? Red is supposed to capture the green in the next step, but unfortunately it captures only some modes, but not all the modes. And the Jensen equality is symmetric, therefore doesn't make any differences in impacting direction. So now you'll probably see why the GAN image are sharp, right? Sharp because it is about capturing some of the major modes in the high fidelity way in my learned posterior or in my learned inference model. Therefore, when I use that inference model, turn around, become a generative model, I'm going to generate pictures from certain modes. Okay. For example, if you can try your experiment, I think nowadays there are many implementations out there. If you throw at the GAN machine, 100 Van Gogh picture, then maybe 10 Rana picture, and maybe a few your picture, you can tell basically what you get out of it. It's not going to look at your style unless you put a lot of your pictures there. Okay, somehow there is a bias, for the popular modes. Okay, are we still together on the GAN model? Hopefully it's intuitive now. Now let's see what is the VAE. Okay, VAE has a very nice looking loss function because it is following the old literature of variational inference. You have this nice kind of a loss function, which is to minimize, this KL and also this part, which is the reconstruction model, remember? And how they connect to the GAN model and also the variational inference or the weak sleep model. Well, it turns out that it's very, very difficult to match because, for example, there is no Y in the VAE model. There isn't an indicator telling you whether it's a fake picture or a true picture, right? Well, then to make these two connections together, I probably need to introduce a Y no matter what. So therefore, one trick is to now introduce a fake discriminator. It's a perfect degenerated parameter discriminator, which basically says that all the pictures are fake because it's all generated, right? But at least symbolically, you will have it. And then you can write down another generative distribution like this, which is very similar to what we see in the GAN model. Okay. There are something that is not done in a GAN model, which is to make an inference about the Z. right? The latent code that is before seeing the real the synthetic data X. In fact, there are variants inside the GAN literature now allow people to even do inference on the Z. So it is doable, but people just don't care. Why I care about that? I care about the X only, right? But in here, in the V literature, Z is important because that's the root of the root to tie the two process of inference model learning and generative model learning together. They are tied together at the Z level. That's why it is important. But in here, I need to take all of them together, Z and Y and X. And therefore, my inference model in here needs to contain, not my generative model in here, need to contain both the Y and the Z, given the X. So with that, it turns out that you can now write down the loss function like we did before in a different way using lemma 2, as in lemma 2. So what's people doing in learning the VE model, it turns out to be equivalent to what's happening here. It is to compute the KL divergence between these two distributions. And this part is the inference model parameterized by theta about what is this? This is the degenerated indicator, whether it is from real data or not. It's degenerated, therefore you don't need to do really inference on that. It's just a placeholder. The Z are your hidden random variables, right? You need to infer that. But you can see that this particular term happens on this side of the equation. In our GAN model, anything that needs to be inferred happens in here. But now it's in here. This is the moving part. The theta keep updating, and it is on here. And this part, the eta model, is the inference model, the authentic inference model that is computing the posterior of the Z given the X. This is more like a generative part of the model. Okay. So just to put it side by side, the most important part is here. Okay. Both the GAN model and the VE model can be reparametrized or reformulated as minimizing a KL divergence between two distributions. One is a reference, one is something you need to update. And in here, you are updating this part, which is to generate the X. And, but it is on the left-hand side of the KL. Okay, and this is the invariant or the reference part. And this part, your model to be updated is in here, the generative model. It is on the right-hand side of the KL divergence. Okay, and whatever here, is the part that is referenced. Okay. Other things are, sometimes they are kind of there's equivalence between the two sides, on other parts. So with that, you kind of start to appreciate the difference between the VE and the GAN model. Again, asymptotically, you can imagine that the KL really inspires the convergence to the reference point. But because of the asymmetry in the I didn't label which one is the GAN model in these two. So the red one is the approximation. The blue one is the reference point. Okay, and the approximation is computed. The red one is computed from either a GAN or a VE loss function or driver. So can you tell me which one is GAN, which one is V? I'm glad that I didn't label it, so now you can guess it. This one is what? Let's speak up. Those who believe it's VE, please raise your hand. Wow, great, congratulations. All right, right? Is that?
Right.
It is? Really? Oh, okay. Well, I wrote a model covering, model missing. I didn't really write it, but good. You know basically, AKL is covering the modes, the other is missing the modes, right? Okay, thank you. You can see I'm lecturing not by reading the slides. That's why I don't even remember what I wrote some time ago. Anyway, good, but you got it. Yeah, so you know, for example, if you want to generate sharp pictures and you want to recreate some character or some figure in your generative machine, you may want to use GAN because it is going to capture very, very high fidelity for those training kind of a major training information. But if you want to give a healthy kind of a blend integration, you use the VAE model. Okay, but now we have a mathematical foundation in there already, right? So you know what's going on. In fact, there are later efforts which allows you to do the so-called compositionality. Compositionality is all about putting all these terms together. Okay, you can, why not just jointly model these two loss functions with a plus? Right, that's doable because we knew how to do each of them. Therefore, you get some kind of combination models. You can graft another more strange loss into the whole thing, and then this whole literature of the deep generative models is actually essentially doing that, either intuitively or subconsciously or intentionally. Okay. All right. So now I think it's time to close. I want to get back to you for a recap of the unification. Let's start from the weak sleep algorithm. Again, weak sleep is about alternatingly optimize learning basically the inference model and also the generative model. And for a convenience reason, the loss function becomes also alternating. They basically use two loss functions. Now, VAE, when you actually just stare at one of the functions in the weak sleep algorithm and replace them with the parameters and the variable names or symbols used in the VAE literature, you can see that what the VAE is doing is to do basically the wake up step. Okay, only one of the steps in the weak sleep algorithm, which is in here. This one is identical to the red equation over there. Okay, but on the other hand, the VAE is not only about learning the Q eta, which is the inference parameter. They also need to learn the theta, which is the generative parameter, right? And in that part, very interesting. They don't really change the goal or switch the KL. Basically, a new term is added to really capture the original KL divergence of the posterior versus the prior. Okay. So that's basically what the VEM is doing. It does not involve the sleep algorithm, and it does not use that reverse KL to approximate the variational free energy. Okay, so that's basically VAE. It sticks to basically that weak phase KL. GAN model is literally the opposite. Okay, if you again plug in all these little symbols in here, replace y by h and phi by lambda by phi, you can see that the equation inside the GAN is equivalent to the sleep step. But also, they need to also learn not only the phi parameter, but also the theta parameter. And in the theta parameter, they start to use, again, a different loss function. Okay, that is in the spirit of the weak sleep. You just swap the loss function. So it basically sticks to minimizing the sleep phase KL. That part isn't changing. Yeah, but it is that's basic determining the direction of the approximation with a reference. You use that direction, the wake sleep, the sleep part direction, and not the wake part. But I think that's it. And of course, using these different loss functions, in two steps, in two alternative steps. So in this formalism, you probably don't see actually the adversarial ever exist. There is no kind of adversary. It's just a single clean equation that helps to really unify some kind of ambiguity, because sometimes people play up that adversarial part to be a very, very kind of a different, mathematically different mechanism for model. Well, it don't have to be. You can basically use the existing framework to reparametrize and reformulate it, and then you can use the existing technique to still solve it. Okay, so good. That's the end of today's lecture. We see now the GAN models and the VE models are essentially, very, very similar, highly related things. And down the road, you can extrapolate this formalism by adding, more terms, and that gives you a way to analyzing broader class of generative models and variants and create, in fact, all these new models that I put, in the literature. I think that's the end of today.